All right, now that we hopefully have a solid understanding of the fundamental theorem of calculus, let's actually start applying it. So before I talk about the start plus accumulation method, let's make sure that we know how to evaluate definite integrals. Okay, so let's start with this first problem here. So number one, starting with something fairly basic. So we're going to start by finding the antiderivative of 3 plus 2x, or that is to say the indefinite integral of 3 plus 2x. So we're going to go ahead and integrate each term. So the integral of 3 is simply 3x. The integral of 2x is going to be 2x. We're going to increment that power, so that's 2, and then divide everything by 2, and that just simplifies nicely to just x squared. Okay? Now, the fundamental theorem of calculus says we're going to find this exact value of this definite integral, we're going to evaluate now our antiderivative at our upper bound, and then also evaluate it at our lower bound and subtract the two. So I'm going to use this kind of vertical line here oftentimes. You might also see something like a bracket. They're both the same thing. So let's go ahead and evaluate this integral now at our upper bound. So 3 times 5 plus 5 squared. So that's going to be our upper bound. I'll put this in a bracket here. And then we're going to subtract this same integral evaluated at our lower bound. So 3 times 2 plus 2 squared, all of that. So that just gives us 15 plus 25, that's 40, minus 6 plus 4, that's 10. So we would say that this is equal to 40. Or excuse me, 30. I know my math. And at some point, as we're going through these problems, if you want to go ahead and check your answers, then definitely you can use a calculator and also just get increasingly fluent with how to use your calculator to evaluate integrals. Okay. Let me just do one more here. Let's try something like this. Let's try to find the definite integral of sine x from these bounds, from negative pi over 3 to pi over 3. Okay. So the antiderivative of cosine is negative cosine. And the antiderivative of sine, excuse me, is negative cosine. We're going to evaluate it at pi over 3 and negative pi over 3. This is going to then give me negative cosine of pi over 3 is going to be negative 1/2. And then from there, we're going to subtract cosine of negative pi over 3, which is also 1/2. So we're going to subtract minus negative 1/2, since we had a negative in front of the cosine, and that's going to be equal to 0. Okay, so try the next two problems on your own, and hopefully you get the idea. We're kind of doing the same thing over and over again. Now, if we go back to our fundamental theorem of calculus, we can say the following. We know that the antiderivative of some function whose derivative is known, or the antiderivative of a derivative, is this function f evaluated at the upper bound minus the function evaluated at the lower bound. Now, if I simply isolate f of b, that is to say, move this negative f of a over to the other side, we can rewrite f of b as equal to f of a plus this definite integral of this function. And this is often known as the start plus accumulation method, and it's a way of finding the value of a function by finding the integral of some derivative plus that starting function's value. Okay, so let's do an example just to make sure that this makes sense for us. Let's start with something like this problem here. Let's suppose we were given the derivative of a function, and we know that function's output at 0. Can we find what f of 2 is? Can we find f of 2? So to set this up, we would say f of 2, we're trying to find f of 2, is going to be equal to f of 0 plus the integral of our derivative, so 3x squared, plus 3, all of that dx. What is f of 0? We're told it's 4. Let's evaluate this antiderivative now, or let's find the antiderivative, I should say. That's going to be x cubed plus 3x, or the integral of that. And we're evaluating it from 0 to 2. Well, if I evaluate this integral at 2, that's going to be 8 plus 6. Let me actually just write that, 8 plus 6. Then I'm going to subtract this integral evaluated at 0, and all of that is just going to be equal to 0, and I plug that in. And this comes out to be 18. Right? Now, compare that to what we did previously with this. Let me just write this in red. What did we do previously for these types of problems? Well, previously, we would have to find the antiderivative, which we already know. We just found that was x cubed plus 3x plus some constant. Then we would plug in this point here. 4 is equal to 0 plus 0 plus c, and then we would do that to solve for c. And then we can say, all right, now that we know what c is, our function clearly is just f of x is equal to x cubed plus 3x plus 4. And then we would have to plug in f of 2 to find what the value is when we plug in 2. So 2 cubed plus 3 times 2 plus 4. And this is all equal to the same thing. Okay? So it's just another way of doing this, but it is one of the applications of the fundamental theorem of calculus. Okay? All right. So now that we've talked about the start plus accumulation method, let's move on to finding the integral of an absolute value function. So the integral of an absolute value function, it requires that we split the integral at any location where the graph of the non-absolute value function would dip below the x-axis. So let's start with a basic example before we do something a little bit more difficult. So let's start with something like the absolute value of x. Well, we already know what this graph looks like. The absolute value of x is going to look something like this. And I'm just going to cut it off from, no, that was really nice. I'm just going to cut this off from -2 going to +3. Okay, so to find the area, let me just kind of zoom in here. Define the area, the side area underneath this curve. Since this is an absolute value function, I would find this, and I would add these up. Now we could do that. Now, unfortunately for us, it's not always going to be that straightforward. So what we want to also look at is what would the non-absolute value of this function look like? That is to say that non-absolute value of this function is just simply x. So when f of x is equal to x, what does that look like? So f of x is equal to x, and I'll just write here, this is f of x is equal to the absolute value of x. Well, from -2 to +3, we would have the following here. And I'm just going to highlight that since this is dipping below the x-axis here, this is red. And then since this is above the x-axis here, this is blue. Okay? So notice, where did my non-absolute value function dip below the x-axis? Right here at x is equal to 0. So what that means for us, to evaluate this integral from -2 to the absolute value of x from -2 to +3, we will do the following. We'll write this as, move this here so we can see this, the integral from -2 to 0. I'm going to create two separate integrals here. Now, what is the function that we're evaluating from -2 to 0? We'll go back to our absolute value function. What is the function here from, let me change this color, from -2 to 0? It is going to be operating as -x dx. And then to that, I'm going to add the integral from 0 to +3 of, let me use a different color here, of positive x. This function behaves as positive x. So I'm going to be integrating this dx. And this is pretty straightforward. This is going to give us -x squared over 2. We're going to evaluate that from 0 to 2. And then we're going to evaluate now, or integrate x, which is just x squared over 2, evaluated from 0 to 3. If we add these up, this would just be -2, well, let's see. Oh, I switched these around, didn't I? I apologize. This should have been from -2 to 0. Sorry about that. So we're going to have 0 here minus this integral evaluated at -2. -2 squared is +4, but we have a negative in front of it. So -4 divided by 2 is -2. So all that's just giving us +2. And then we're going to add to that this integral evaluated at 3. So 9 over 2 minus 0. So 2 plus 4.5, it's going to give us 6.5. So that represents the area underneath this absolute value function. The way we would have to do it is to split this up here. Now that we understand that, this actually has some applications. When we are working with functions, now that we understand the absolute value is going to give us the total area irrespective of sign, we can now just find the integral of the absolute value of the function to find total distance. When I actually care about the net change in distance or your displacement, I would just evaluate that function as is. So if you have a function where you're going 2 steps forward and then 1 step back, this total distance would be 3. Its displacement would be +1. Okay, and way back in Unit 1, we would do this just by counting out the steps, but now we can actually use integration to do this a bit more efficiently. Okay, all right, so let's try this problem here, and pause the video right now and work through this. Well, if we look at these functions here, let me just quickly draw the graphs of these functions to make sure that we make sense of this. We know that the absolute value of x squared minus 1 looks like this. So let me just draw this from -1 to +1. The absolute value of x squared minus 1 is going to kind of do something like this. +1 here. All right, so this is kind of what our graph looks like here. This is the absolute value of x squared minus 1. Now compare that to the non-absolute value of this function, and I'm doing this because I want to see where it's dipping below the x-axis. So just x squared minus 1, the non-absolute value, would look something like this at -1, +1. Well, where does it dip below the x-axis? Right here at from 0 to +1. Okay, so what we want to find is the absolute value of the area. Let me go ahead and just change this color here. The absolute value of the area from, or the integral of the absolute value function, or the area underneath the absolute value function curve from 0 to 3, which would be this area plus this area here as we go towards 3. And this is not a great graph, but you get the idea. Since I know that my function, the non-absolute value function, dips below the x-axis at 1, I can set up my integrals as follows. I can say my first integral, actually let's go back to black. My first integral is going to go from 0 to 1. I'm going to stop at 1 because that's where it dips below the x-axis. And that's, it's behaving as 1 minus x squared. Okay, so this function here is 1 minus x squared. Okay, so again, vertex of 1, dipping below, and then it's a negative quadratic x squared dx. And then the rest of it is going to go from 1 to 3, and it's going to then behave like x squared minus 1 dx. And then once we integrate that, we're just going to go ahead and write x minus x cubed over 3 from 0 to 1 plus x cubed over 3 minus x evaluated from 1 to 3. And this comes out to exactly 22 over 3. Okay? All right. Well, hopefully this video helps work out some of the applications for the fundamental theorem of calculus, specifically how to evaluate definite integrals, the start plus accumulation method, and integrating absolute value integrals. In the next video, we'll do some practice problems where we are applying the second fundamental theorem of calculus and find the average value of a function.